In this video, we will take a look at another version of calculus which is called discrete calculus. Discrete calculus is different from the continuous calculus that we have studied before. Um, in continuous calculus, we focus on what is called a function. A function can be thought of as a machine that takes as its input a real number and outputs another real number. Like for example, the function f of x equal x squared. When you plug in 0, you get 0. 0 square, which is 0. When you plug 1, 1 squared is 1. When you plug 2, 2 squared is 4. So 0 will give us 0. 1 will give us 1. 2 will give us 4. And so on. 5 square is 25. This is called a continuous function because we can plug also half and 1/2 and 2/3. Any number we can get it as an input. While the version of discrete calculus focuses on a sequence. A sequence is like a function, but it has a restriction that its input must be a natural number. Like un, we write it as un instead of f of x. N represents a natural number to remind us that we have to input a natural number. If we take a look at the sequence un equals n squared, this means that the first the first term, which is at 0 equals 0, we plug in equals 0, so we get 0. 1 we get 1, 2 we get 4, 3 we get 9, 4 we get 16. So we can plot it on a graph like this, which will have dots to represent the graph output of the sequence. Since we don't since we can't input a fraction or real number, you we will represent only dots to represent the graph. While in continuous calculus, the line is continuous all over the domain. We will then look at similarities between calculus and discrete calculus. In continuous calculus, we have the slope, which is dy by dx, which is defined as limit as delta x goes to 0, f of x plus delta x minus f of x over delta x, which is the change in output relative to the change in input as the change in input approaches 0. This is the minimum change in input can be as small as 0. It can be 0.01, 0.001. We will we will always find another change that is smaller than what we chose. So we take a limit as this change approaches 0. Like this graph, the slope here gives us the tangent vector, the tangent line. Slope in discrete calculus, on the other hand, we have the smallest change in input in discrete calculus is 1. We don't have fraction input, so the step size of our input is 1. So we will have discrete values which have a change in input equals to 1. So when we have a change in output, which is the change in the function, divided by the change of input, which is 1, so dividing by 1 is the same as not writing it, because anything divided by 1 is itself. We will have two definitions for the difference, which is the discrete version of the derivative in continuous calculus. Difference could be forward difference or backward difference. What is forward difference? Forward difference is taking the the next input minus the input that you are in. Yeah, the output, the next output minus the output that you are present here. So we take the derivative at here. So we take the output minus the output in the current place. While the backward difference, we take the output in the current place minus the output in the previous stage, un minus un minus 1, while in forward difference un plus 1 minus un. So we have two differences, not one for forward difference and one for backward difference, and they can be represented as straight lines because we don't have inputs between them to give us what is the function look like between them. How to compute differences? Take a look at this sequence. N here represents the index 0, 1, 2, 3, which is the input. The output here is 3, which is constant. If we take the forward difference, we will take 3 minus 3 to give us this 0. While to get this number, we take 3 minus 3, which gives us this 0, and so on. So we can see a similarity between the difference and derivative. The derivative of a constant is 0. A constant function is 0. Now we will take a look at a linear function, a function that increases linearly with the input. As the input increases, the function increases. This increases by 3 each time, which can be represented as a function un equals 3n. When you plug n equals 0, you get 0. When you plug in 1, you will get 3, and so on. So if you take the forward difference, you will have 3 minus 0, which gives us 3. So we put 3 here, and so on. We'll get that all the outputs in the difference will be 3, which can be computed from here. We have un equals 3n. Delta u of un equals un plus 1 minus un. Okay, this is equal to 3. Un plus 1 is 3 في n multiplied by n plus 1, because we have n plus 1, so we plug in n plus 1 minus un, which is 3n. 3n plus 1 يبقى okay, this is 3n plus 3 minus 3n, which is equal to 3, which is constant. That is why delta u of n equals 3. Now we will compute the difference for a quadratic function. U of n equals n squared. U of n equals n squared. We compute the difference as follows. We take un plus 1 minus un. Un plus 1 is n plus 1, which is the input, squared, minus n squared, equals, if we open the bracket, n squared plus 2n plus 1 minus n squared, which is equal to 2n plus 1. This is very similar to derivative, but we have a positive one increased. We don't have in continuous calculus. In continuous calculus, the derivative of x squared is 2x, while here it is 2n plus 1, which we can see here from the table 0, 1, 4, 9, 16. If we take the difference, 1 minus 0 equal 1, 4 minus 1 equals 3, 9 minus 4 equal 5, 16 minus 9 equals 7, 25 minus 16 equal 9, and so on. So we are almost like the continuous calculus, but there is a small difference. In order to eliminate this difference, we will introduce what is called a falling power. A falling power is defined as n to the falling k equals n multiplied by n minus 1 multiplied by n minus 2 and so on until n minus k plus 1. We can rewrite this to be um, more obvious, that n can be wrote as n minus 1, n minus 1 could be n minus 1 still, and so on until n minus k minus 1. If we take a bracket here, we'll get k minus 1, which means we have 0, 1, 2 until k minus 1, which will be k terms. So these are k terms. The starting of it is n, so n to the falling k will start at n and decrease by 1 each term, and the number of terms overall is k terms to compute it. What is the main advantage of this? The main advantage of this, if we take the forward difference for n to the falling k, it will be equal to n plus 1 to the falling k minus n to the falling k by definition. If we compute n plus 1 to the falling k, we'll get n plus 1, n minus 1, 2 k terms. N plus 1 is the first, and the power here, the falling power here, represents the number of terms we take. We will get the following term. If we subtract from it n to the falling k, n of n minus 1 multiplied by n minus 2 until n minus k plus 1, we can get n multiplied by n minus 1 multiplied by n minus 2 until n minus k plus 2. We can take it as a common factor because it is presented in the two terms. We will get from here, from the first term, n plus 1, all the rest of the terms are taken in the common factor, and what we left with is n plus 1. And the second term we will get n minus k plus 1. N with negative sign will cancel out with the n. 1 with the negative sign will cancel out with the 1. Negative multiplied by negative will be positive k n to the falling k minus 1, which is exactly like when we take the derivative of the original power. When we take the derivative of original power, it's like taking the difference of a falling power. We can also introduce the definition for the falling power for negative values by this definition. I will leave it to you to show that the difference here can be represented as the same equation as the continuous version of it.